The tangent plane to a surface that's been parameterized, so it's given by r of uv, contains the tangent vectors, the partial of r with respect to u and the partial of r with respect to v, and has as its normal vector ru cross rv. We're going to illustrate this with an example here. Find the equation of the tangent plane to x equals u squared plus 1, y equals v cubed plus 1, z equals u plus v at the point 5, 2, 3. This is rather an exotic surface. We don't need to know what the surface looks like. I'll show you a visual so that we can hash out the ideas here. But first we're going to express the surface as a vector function here. R of uv is equal to u squared plus 1, v cubed plus 1, u plus v. Well, here's the surface. Grid lines holding u constant hold x constant, and so give us these kind of cubic looking curves. It should make sense that they're cubic given that y is v cubed plus 1. Holding v constant means we're holding y constant, and so we get these parabolic curves that are parallel to the x-axis. The idea here, at the point 5, 2, 3, there exists a tangent plane. I'll just draw something here for us to hang our hats on. And then let's explore this assertion that the surface contains the tangent vectors RU and RV. RU would be a tangent vector that we get by holding V constant. And so it should point in a direction that's parallel-ish, whatever, to the parabolas. So we're going to call that RU. And then the partial of R with respect to V is going to hold U constant, and so should point kind of in the direction-ish of the cubic curves. The tangent plane contains those two vectors. The normal vector to the tangent plane is going to be the cross product, RU cross RV, and of course will contain the point 5, 2, 3. Now, to be clear, in order for you to do the work, you don't have to graph the function or the surface. You don't need the visual here. I just gave it to you so that you could see where our work is going to come from. For you, the mechanics are we need the partial of r with respect to u. And that partial, so r with respect to u of uv is going to be 2u, 0, 1, differentiating the component functions with respect to u. And then our v of uv is going to be 0, 3v squared, 1, again differentiating the component functions of the surface with respect to v. Now we were given this point. The point is 5, 2, 3. But it's up to us to figure out what values of u and v correspond to 5, 2, 3, because look, our partials only take in u and v, so we need to know what u and v are. Well, 5 must equal u squared plus 1, and 2 must equal v cubed plus 1, just equating the x component of r with the point, the x coordinate of the point, and the y component of r with the y coordinate of the point. By inspection, we can figure out that u is equal to 2 and v is equal to 1. We might say, wait, u could be plus or minus 2. Yeah, but u plus v has to be 3, and so we need these values here. So we can immediately go to ru of 2, 1 is equal to 4, 0, 1, and rv of 2, 1 is equal to 0, 3, 1. And we can use those in our cross product. So RU at 2, 1 cross RV at 2, 1 is going to be IJK 4, 0, 1, 0, 3, 1. And you can confirm that that'll give us -3, 4, -12. So I'm actually going to use 3, 4, -12. And then the point we were given is 5, 2, 3. We put that together the way we know how to do for the equation of a plane. 3 times the quantity of x minus 5 plus 4 times the quantity of y minus 2 minus 12 times the quantity of z minus 3 is equal to 0. Simplifying this equation will give us 3x plus 4y minus 12z is equal to negative 13, and there's the equation of our tangent plane.